we all pretty much have down the idea of a normal distribution and the way that the z-score is related to well, is a measure of the standard deviations above and below the mean, and how that can describe an area, or an area under the normal distribution. And that area can be interpreted as the proportion, the percentage of people that are within that area, or it can be, if we're going to take a sample from that normal distribution, it can be interpreted as the probability of sampling, of finding someone when we take a random sample from that area of the normal distribution. In other words, lower than 3 standard deviations away, or more than 2 standard deviations above, or between 2 below and 2 above, and so on and so forth. I think we got that pretty much down. But now we've complicated things a little bit, because it's a good complication. This complication will help us understand the nature of sample distributions. And that's important to us because in statistics, we're very rarely dealing with an entire population that we know all about or that we've sampled completely. We're almost always dealing with a small sample from a larger population. So it's important that we understand the dynamics of sampling from random samples from a population. And that's where the central limit comes in. Central limit theorem comes in. Okay, a couple of elements that are important to us about the central limit theorem. Central limit theorem basically tells us that if we start out with a normal distribution, like for instance, this distribution right here might be interpreted, let's say, to be the average blood pressure for healthy 20-year-olds. And let's say the average is 75. Okay, and I might know that within this population that the standard deviation of blood pressure is equal to, I'm going to say 5. I'll make up a number 5. Okay, so I know that 95% of, and I'll call this female college students, college age students. That really does, I guess college age is not very specific these days, right? We're evidence of that, aren't we? Female college age students, I'll put an age range of here, 18 to 22. Okay, and that the mean for that population is 75 and the standard deviation is 5. Well, I can, as I said, I can interpret this population distribution as telling me that 95% of the population of these college students has blood pressure between 2 standard deviations below the mean of 75 and 2 above. And since the standard deviation is 5, that would be 65 and 85. Okay, and the chances that I would pick, since this is 95% in here, the chances that if I randomly selected one person from this population, the chances that I would pick someone that had a blood pressure below 65 is going to be the area or proportion of the people in this population that have blood pressures below 65, and that's going to be 2.5%. Right? So we know that dynamic. We understand that dynamic when we deal with the population. Now, let's carry that over to if we take a sample from this population. We really rarely would know that this is really true for every female college-age student, and that this is the standard deviation for every female college-age student in, say, in the state or the country or something like that. We would very rarely know that kind of information. We would really be blind. We wouldn't know what this number is, and we wouldn't know what this number is. The only clue that we would have about this distribution is if we took a sample from this distribution. And if I took a sample from this distribution, I'm going to pick out a sample of, say, 25 students. If I were to pick out a sample from this sample of 25 randomly selected students from this distribution, well, I would expect the average to approximate the average that I don't know of this population. So I'd expect it to be somewhere. I'm going to call it X bar instead of calling it mu like I would call this 75 if I knew it. I'm going to call it X bar. So I'm going to say if I took that first sample, that the mean would be 75. 75. Maybe I got lucky, I hit it right on the head just that one time. If I did it again, maybe I'd get a 73. If I did it again, maybe I'd get an 81. If I did it again, maybe I'd get a 76, and so on and so forth. If I did that over and over again, I would get a new distribution, right? And that new distribution of all these repeated sample means is also going to be normally distributed, right? Except this time, because by the nature of sampling repeatedly over and over again, half the time I'm likely to get a mean below 75 and half in this population, half above 75. So the mean that I get for all these repeated samples, right, say do it many times, the mean that I would expect to get is going to be 75, just like the mean of the population. Now, the thing here is, though, is that the standard deviation of this population might have been 5, but now that's the spread for all of the individual blood pressures, including some people that were below 65 or above 85. Now, the likelihood of me sampling 25 people from this distribution, getting all of them in this little area down here, randomly sampling, right, is very, very super unlikely. So I can see intuitively that this sample distribution now is going to be narrower than the spread of the actual population. And we have a formula that's part of the central limit theorem that helps us determine what that sample distribution looks like. Okay, we expect the mean of that sample distribution to approximate the mean of the population, and we expect the standard deviation of this sample of these sample distributions to be smaller than the standard deviation of the population. We expect to be a smaller number because this should be narrower, right, by the nature of this sampling operation, right? Well, we're going to make up a new name for it, this new number, since it's not approximating the standard deviation, it's actually smaller. We're going to call it the standard error. And we're going to be able to calculate that and say that that's equal to the standard deviation of the population divided by the square root of the sample size. Well, I just went through this whole thing where I told you we very rarely know the standard deviation of the population. For the time being, as a learning exercise, we're going to make believe that there are cases where we know the population standard deviation. In fact, there's occasional cases where we may not know written in gold, we may not know the population standard deviation, but we may have a good enough appreciation for it or a good enough estimate of it from previous studies or very large studies to kind of guess at it and think that we know it pretty well. Okay, but for the moment, we're just going to make believe that we actually know it. So that's going to be, in this case, the mean would be 75, and the standard deviation of this distribution of the sample means is going to be equal to the standard deviation of the population over the square root of the sample size. It's going to be equal to 5 divided by 5. It's going to be equal to 1. So now, if I were to take repeated samples of size 25 from this population, well, what would happen now is 95% of the time, each time that I did that, I would get a result. I would get a result between 73 and 77. 2 standard errors above and 2 standard errors below. Okay, that would happen 95% of the time. And I would only get if I randomly selected 25 from this population, I would expect to only get a sample that was below 73. It's mean that was below 73. I would only expect that to happen 2.5% of the time. And above 77, I would only expect that to happen 2.5% of the time, right? Because the other 95% is within this range. So 95% of the time, I would expect it to be in here. About 5% of the time, I would expect that might come across a result that's higher or lower than that range. Okay, so that's our starting point about our central limit theorem. Okay, one other thing about central limit theorem. Sometimes the way the central limit theorem works, because we're taking repeated random samples, we can have a sample distribution that maybe is a little bit skewed. And even though the sample distribution is skewed, if the sample size is big enough, our repeated sample means their distribution is symmetrical and not so skewed, right? So we can assume it's not skewed. So this, just because a population may not be perfectly normally distributed, we can make certain assumptions about the sample distribution that will help us when we have to do some calculations later on, because it may be more normally distributed than the actual original population is. In fact, it's almost certainly going to be that way. Okay, so how do you guys feel about that? I'm going to hit you on a scale of 1 to 10 again to give me some feedback. 0. Okay, we got a 10. We got 10. Oh, this is great. I love this. This is terrific. That's what I like to hear. Okay, so now we're going to take the next step. Now that we understand this about sample distribution,